So we left off yesterday here. We're doing the example problem number 1. Example problem number 1 in your set of notes. And we've got our seesaw, or our meter stick drawn. We've labeled the forces. We've labeled the lever arms. We've indicated all of our knowns. We've identified our unknown. Now, something I do want to point out here in the beginning. Why do we have to use rotation here? Why can't we just use Newton's laws for translational motion to solve for mass of the meter stick? Can anyone tell me? Because if I could just write an equation with Newton's first law for normal motion, which we're used to, which just says that this force equals the sum of those 3 forces, then I could just solve it for MS and be done with it and not have to worry about rotation.
Because the motion begins to be in a circle?
No, because we are in equilibrium, right? We've balanced this. If this was a lab, we've set the masses so that everything is balanced, so nothing's going to move. How many unknowns do I have in that diagram there? I know the masses of everything. MS is an unknown?
And force normal.
And the normal force, or force normal. So we have 2 unknowns. There's no x components here, so we can't do net force in the x direction like we used to. So that we can only get one equation from Newton's laws for translational motion, and one equation is not enough because we have 2 unknowns. So that's why we got to use Newton's laws for rotational motion in order to generate an equation, another equation. But what's nice about Newton's laws for rotation is that if I chose this point as my axis of rotation, then I've said that, well, the normal force now creates 0 torque. Remember this. This will make your life easier. Remember the definition of torque is force times lever arm times the sine of the angle between them. All right, well, if the sine of the angle between the force and the lever arm is 0, i.e. if the angle is 0 or 180, then the torque is 0. Again, that's like grabbing a door handle and pushing it towards the hinge or pulling it away from the hinge and expecting it to open or shut. It's not going to happen. Or if the lever arm is 0, then the resulting torque is 0. So wherever you choose your axis of rotation, any force that acts on that axis of rotation will create 0 torque. And will drop out of the equation, the resulting equation that you generate when you apply Newton's laws for rotational motion. Rotational equilibrium in this case. So when I write my equation for Newton's second law, or Newton's first law for rotational motion, the normal force isn't even going to be in there, because it's not going to create any torque. Okay. So I don't even need to use Newton's laws for translational motion, because the one equation that I can generate using the torques here, or using the torques from these forces, will be enough to solve for my unknown. Okay. So again, those are the steps. You draw your diagram. You have to draw the actual object, though, because it's not just the forces that are important now. It's where on the object those forces act. You draw your lever arms from your chosen axis of rotation, and then you set up your equation. Right? You choose your axis of rotation, draw your lever arms, draw your forces, draw the actual object, and then apply Newton's laws for rotation. I just want to stress again, the choice of the axis of rotation. We had a good conversation about this last period. Your choice of axis of rotation is completely arbitrary. You can pick any axis of rotation you want. Nothing's actually rotating here. Right? There's nothing rotating. So nothing is actually rotating about any axis. We're actually free to choose whatever axis of rotation we want. I can choose where this force is, or where that force is, or where that force is. I can choose a point over here. I can choose this as my axis of rotation for this system. Now, that wouldn't be very convenient, though, because remember, the lever arms are drawn from the axis of rotation to the force, to the application point of the force. So the lever arms would all be up this way, and they all have different angles, and it would just be ridiculous. It would be ridiculously convoluted, but it would work. It would work. Note that when I choose this axis of rotation, M1G creates positive torque, MSG and M2G create negative torque. Those torques balance each other. If I was to choose this as my axis of rotation, the point M2G, Well, then I have the normal force creating negative torque, and the two weight forces M1G and MSG would be creating positive torque. Those torques would balance. If you don't believe me, check it. When you do the problems on the quest assignment, choose an axis of rotation to calculate an answer, and then choose a different axis of rotation for the same situation and make the same calculations. You'll get the same answers, the same results. I guarantee it. I promise you. Okay. But you want to choose a convenient one. In this case, you would have to choose the normal force, or the fulcrum here, because you're trying to get rid of the unknown from the equation. By choosing this as your axis of rotation, you're eliminating the normal force from the resulting equation because its lever arm is 0, so its torque is 0, leaving MS as your only unknown. Does that make sense? You got to be think strategery, right? Strategery. All right, so I got all that done, and I'm going to go ahead and write my statement of Newton's, technically Newton's second law, but where the angular acceleration is 0, so it's just Newton's first law. An object with no net torque will not accelerate angularly. So net torque equals 0. I have a positive torque from M1G. How do I know it's positive? Because it wants to cause counterclockwise rotation, which in the standard coordinate F system for rotation is positive, the positive direction. As a reminder, in pre-cal or calculus, positive x-axis, you measure angles counterclockwise as positive, clockwise as negative. So M1G is going to create positive torque, and I use this equation to write its torque. So the torque, and I'll write it like this. The torque for M1G, that's the positive torque, and then I have these two are negative torques because they want to cause clockwise rotation. So I have minus the torque due to the weight force of the meter stick, minus the torque due to the weight force of M2. That equals 0. And then I have to use my equation for torque to plug in the expressions for each of the 3 relevant torques. I could have put plus the torque due to the normal force, but the torque due to the normal force is normal force times 0 times the sine of the angle. And what's the angle between a 0 vector and another vector? It doesn't make sense. So there's no torque. There's just 0 torque. So M1G, and notice the angles here. I didn't label the angles. The angles between all of these lever arms and the forces are all 90 degrees. And we all know that the sine of 90 degrees is 1. So I can leave the sine of the angle out of all 3 of these because they're all, the sine of all the angles is going to be 1. So the torque created by the weight of M1 is simply M1G times that lever arm, R1. And remember, we got those lever arms yesterday we had to dig into it and actually analyze a little bit because it didn't give us those values explicitly. We had to do a little mental math to figure out what those were. But it wasn't too bad. Minus the torque due to the weight force of the sine, so that's MSG, times the weight force of the sine's lever arm, which is RS. I don't have a G there. And then and remember, both these are times the sine of the angle, but the angle's 90, so the sine of the angle is 1. Minus the torque due to M2G, so that's going to be minus M2G is the force, times the lever arm, which I called R2, equals 0. And now everything in this equation is known except for the mass of the meter stick. But we can make a simplification. What's my simplification?
Get rid of the acceleration due to gravity.
Yeah. Everyone brought G to the party. And remember, this is why the fact that, literally, the fact that happens is why triple beam balances give you masses and not weights. Weight is mg. Mass is just m. That's why triple beam balances will work regardless of what planet you're on. So when you're on a different planet today doing your singing, take a triple beam balance with you. It'll still work. What are you singing?
J songs.
What songs? You don't know?
Oh my gosh.
Oh man, you better figure that out. It's fine. It's fine. It's fine. Okay. So I got M1 times R1 minus MS times RS minus M2 times R2 equals 0. I'm looking for MS, so I'm just going to add this term to both sides, right? I'm going to add MSRS to both sides. so it becomes positive. And then I'm going to write the right side here, I'm going to write it on the left side, so I get MSRS equals M1R1 minus M2R2. And then divide by lever arm for the meter stick. And I get that mass of the meter stick is going to be M1R1 minus M2R2 divided by RS. This is the kind of physics, by the way, that goes on when they're designing these and how far you got to move the mass to create the torque to offset the thing that you're trying to measure. This is literally the physics that goes into that. M1, 0.8, R1, 0.2, minus M2, 0.35, R2, 0.35, divided by RS, 0.15. And you do that in your head, right, Kyle?
Yeah, it's 0.25.
Is it really?
Yeah.
Oh, okay. Thanks.
I did it as you were talking.
Okay.
In his head, obviously.
0.25 kilograms. There you go.
What, did I scare you?
Wow, impressive. I've had classes in the past where I'd say that and they would just guess. And then occasionally someone will be like really close.
Yeah.
It's interesting. Any questions? Note what we could do now. If there's a number B to this question and it said what's the normal force, now we can use Newton's laws for translational motion to figure out what the normal force is. Because now we know all three weight forces, or at least all three masses. We always know G. So the sum of the three weight forces has to equal the normal force, right? So we can calculate the normal force after we do that. But notice, with Newton's laws for translation, only one equation can be generated for this situation. And we have two unknowns. So we must use something to generate the second equation. That something is Newton's laws for rotation. Which, again, we can apply whether the system's rotating or not. And we can choose whatever axis of rotation we want. Okay? Again, you want to be strategic, though. Got to think critically. Use your gray matter. Any questions? Let's move on to example 2 then. Directly below example 1. And this problem is a very, very common introductory engineering problem and physics problem, obviously. And it has to do with hanging a sign from a beam. So here's my sign, here's my beam, and then that beam is supported by an axis or a hinge, right, that connects it. Usually you don't want a beam rigidly fastened to the wall because then if it gets stressed, then it'll break, right, if it's attached.
The lever force is what's really fall.
What's that?
Like the lever force, because if it's the farther out it is, the easier it is to fall.
Right, well you want the tension is going to help offset that. But you also want a hinge here so that it can move just a little bit, especially if you got a very large object that's made of metal, because as metal changes temperature, it contracts and flexes, and so you want it to be able to move a little bit. Has anyone ever been to San Francisco? You know the Golden Gate Bridge?
Yeah.
On a hot summer day, the Golden Gate Bridge is 6 feet higher than it is on a cold winter day. It actually moves 6 feet.
Wasn't there a bridge that like collapsed on itself?
Yeah, that has to do with simple harmonic motion and winds, the Tacoma Narrows Bridge. Yeah. If we were still doing our unit on waves, I definitely would have brought that up when we would have analyzed that a little bit. Because it's, sadly, no, I won't even bring it up because it's sad. Tacoma Narrows Bridge is pretty cool watching it collapse because it like twists like a wave. It's really cool looking. I mean, I'm sure people got fired over it because bad engineering, you lose a lot of money. You mess up when you design a sign and you don't order a cable that can support the tension that it needs to, then it can break and people can get hurt. People can get worse. And then when that happens, you can be sued if you're an engineer. You can go to jail. You can go to prison. So you gotta be careful. You sign off on official documents when you say, this is safe. I've done the engineering. I've done the physics. I know what's going on. So anyway, long story short, very common. you got a hinge that the beam is attached to. You hang a sign from it, and then you got to know what tension needs to be based on whatever angle you need for the connections, the angle between the beam and the string, the rope itself or the cable itself. You got to know what tension is going to be on this cable so you can buy the right cable, right? Obviously, if the tension you need is like 1,000 newtons, obviously you don't want to buy a 1,000 Newton cable, right? You'd want to buy like a 14 or 1,500 Newton cable just to be safe. Some crazy teenager could come along and jump up and grab onto it and hang off of it, you know. So, example 2 is dealing with just such a situation. Back in the day when we did labs, you know, real labs, we would give you a setup like that, and you'd have to determine the tension. You'd have to calculate the tension and compare it to what the spring scale actually reads, and generally they're pretty close. Yeah, we used to do labs in physics class. All right, so here's our pole. A uniform metal beam with a mass of 20 kilograms extends horizontally from a pole as shown to the right. A support cable of negligible mass from the far end of the beam to the pole, forming a 40-degree angle with the beam. The beam has a sign with a mass of 5 kilograms hanging from the end of it. Find the tension in the cable that helps support the beam and the sign. All right, so they left it off of this, but because usually in the problems that you'll see in the textbooks, there's a hinge there that the beam is attached to, kind of like in the setup that I got there. And then we got the string that's attached to the very end. It doesn't need to be attached to the very end. Sometimes it's not. In this particular problem, it is. Usually it is.
Does it help if it's at the very end? Does that change anything?
What's that?
If it's at the very end, does that change anything?
Oh, yeah. If it's not, yeah. Like right here. Usually the cable's attached to the end or close to it. But then the sign can be hung from anywhere. And notice that's a little different now. It's hanging down a little more there. If I hang it from here, it's hanging down a little less, right? And so if you want it to be completely horizontal, you gotta be careful there. So depending on where you actually hang the sign, things will change, as we'll see.
Does it matter where you tether it, like where you put the cable? Does that change anything?
No, the angle is what's gonna matter.
Oh. That would change things.
And we'll see that. We'll see that as we go through this problem. So I got my sign here. It's bigger than that. Here's my sign. Here's your sign. Okay. So there's my sign. I got my beam. And then this is just the pole that everything's attached to. Okay. Pretend it's straight. And then we got an angle here, theta. Okay. And part A says find the tension in the cable. And so here's my actual setup, but I'm going to draw the free body diagram separately. And I'm dealing with the beam. I'm dealing with the forces that act on the beam, okay? Because the tension force acts on the beam. The weight force of the sign acts on the beam. The forces that the axle exerts, the hinge exerts on the beam, act on the beam. The weight force of the beam itself acts on the beam. And so I draw the free body diagram for the beam. So there's the beam. I got a weight force, MBG. I got a weight force of the sign hanging off the end. Call that MSG. I got a tension force that's pulling up at a 40-degree angle this way, FT. That cannot be, actually MSG should be shorter. It should be 1/4 actually, whatever. These can't be the only three forces, though. If these were the only three forces, the beam would necessarily be accelerating this way, right? Tension has an x component that points to the left, which means there must be some force preventing that motion to the left that's pointing to the right. What do you think is the agent of that force? Yeah, the pull. Or the hinge, depending on, if you're reading this problem explicitly, then yeah, it's the pull pushing this way, okay? Think about this too, though. If I was to pull the pin out of the hinge, the beam is going to start moving this way a little bit because there is the X component of the tension. Things will change as it happens. The direction of the tension force, so that acceleration will change. But immediately after I pull the pin out, it's going to be accelerating this way a little bit. What else is the beam going to do when I pull the hinge out? Won't it just fall? Won't it start falling as soon as I pull the pin out? So doesn't there have to be an upward force on the beam at that point as well? Yeah. So I'll bring this up. We're not there yet, but if you look at part B, it says find the horizontal and vertical components of the force the pull exerts on the metal beam. So in part B, we're actually going to have to find some force components. We're going to have to find this component of the force. And these are normal forces, right? If you have something resting on a hinge, it's essentially just resting on a surface. So that's a normal force. This would be the Y component, but then I would also have the X component of that normal force.
So does that mean that our axis of rotation is at the edge where the beam connects to the pole?
That means that would be a convenient choice for your axis of rotation because then the torques created by those two force components would go away. Okay. Notice, though, that these are components, so the overall normal force is always going to point up and to the right. This is something that engineers always deal with when they're dealing with things of this nature. Okay, if I add these two vectors, I get a net force vector that points up and to the right. And you might ask yourself, I remember asking myself this at some point when I was doing a problem like this, do I need rotation here? Do I need rotational concepts? Because unlike the last problem, I can write an equation for the horizontal forces using Newton's laws for translational motion and an equation for the vertical forces. In the last problem, I can only write an equation for the vertical forces. In this problem, I can write one for the horizontal ones as well because I have horizontal components here. So that's two equations. And notice I know the masses of the beam and the sign. I know G, so my only two unknowns are the tension and the normal force. So it looks like I only have two unknowns. And I can get two equations without having to worry about rotation. The problem is, because if you know the angle, I know this angle here. If you know the angle, and you can calculate one component of the tension, and you also have the angle, you can always find the other component using SOHCAHTOA trigonometry. The normal force, however, this normal force, we do not know the angle. We do not. There's no way of knowing just by direct analysis with the given information what angle this normal force is because we don't know how big each of these components is. So we can't use SOHCAHTOA to say, all right, I know this one, so I can get this one using SOHCAHTOA. I can't do that because I literally don't know the angle. Okay.
Well, but couldn't you say that once you find the force of tension in the y direction, you just do the sum of all of them and find at least either the y or the x component and then offset it with force normals?
So keep that in mind as we go through our solution. Yes, you're asking good questions. Keep that in mind. You're saying, for anyone else, you're saying that can I figure out this component or this component by calculating that component, right? But can we get this component if we don't know that component?
Well, right, but why don't you just use it in the y direction then? Because you know all of the vectors in the y direction apart from the force normal line.
So we can use that to get the tension force in the x direction is what you're saying.
Yes.
Okay, keep that in mind as we go through our solution. Because I'm gonna go ahead and use rotation, and then that will probably come up as we get, because that's what happened last period. Because I didn't bring this up before we started the solution, but then it became obvious later. I don't know, you might have me second guessing myself, I don't know. We'll see. Okay, so bottom line at this point, we have two components of the hinge force or the pull force on the beam that we don't know, and we have a tension force that we don't know. We're looking for the tension force in part A. If I do have these two components here, this would be, as Kyle pointed out, a good choice for our axis of rotation. Yes? Because if I pick that as my axis of rotation, then I've eliminated the torques created by these two components of that hinge force. In which case, I only have these three torques that I need to worry about. Oh, lever arms. Notice I'm not giving the dimensions of the beam. I'm not told how long the beam is. I'm just told this angle. But I'm not told how long the beam is. It's not a problem though, as you'll see. Here's the lever arms. So what do we do to represent quantities that we don't know? We assign a variable. So I'm just going to call the lever arm for MSG L, in which case the lever arm for MBG would be L over 2. Right? It's 1/2. Weight force of the beam, it's a uniform beam. It's drawn right from the center. All right. And so the lever arm for the tension force is also L. Okay. And I'm going to go ahead and apply rotation concepts and say that the net force, this is the bad one. Net torque, the net torque acting on the beam, we want to be 0. If it's not 0 as an engineer, you've messed up and you're putting people's lives in danger. So the net torque we want to be 0. I have 3 torques here, or 3 forces that create torque about this axis of rotation. Which one creates positive torque? Or ones? Which one or ones? Which force or forces create positive torque?
In which direction?
In the standard coordinate axes, which says that clockwise, counterclockwise is positive, clockwise is negative.
Basic force tension was due positive and force normal would be negative.
That's our axis of rotation. If that's our axis of rotation, the normal force doesn't create any torque. But you're right, the tension creates positive torque.
Yeah, okay. They're axes.
So the torque created by the tension force is positive, and then these 2 forces want to cause clockwise rotation, so they're going to create negative torques. So I minus the torque due to MBG, minus the torque due to MSG, equals 0. All right, the tension force torque is going to be the tension force times the lever arm, in this case we just call it L, times the sine of the angle between them. The sine of the angle between them is not 90 degrees, so it's not 1. The sine of the angle is not 1. So we got to keep that all in there. That's going to be the sine of 40 eventually. Minus the torque created by the weight force of the beam itself. So that weight force is MBG. The lever arm is L over 2. But that angle is 90 degrees. So the sine of that angle is going to be 1. So that's it for that one. And then the angle here is also 90 degrees, so the sine of that angle is going to be 1. So the torque created by the sine is going to be minus MSG times the lever arm, in that case, is the full length of the beam, times the sine of 90, which is 1, and all that equals 0. And why don't I need to know the length of the beam itself? Because it cancels out. Everyone brought L to the party. And then at this point, in the interest of time, I'm going to go ahead and add the resulting terms here to this side to get ft sine theta by itself. Ft sine theta is going to be equal to this term. When I add it to the other side is going to be mbg over 2 plus msg. And then I divide both sides by the sine of the angle. So the tension force will be mbg over 2 plus msg, all divided by the sine of theta. If you didn't have numbers here and you were in pre-cal with Mrs. Garcia or Mrs. Burke, you would obviously simplify this a little more, right?
Would that be okay? If
And then
if they were just asking for an equation, would that?
In AP Physics 1, this would be okay.
That'd be okay. Answer. So like if they would find the equation for this, find like a way to solve this.
Yeah, this would be okay.
This one.
All right. So the mass of the bridge was the mass beam. What was the mass of the beam? 20 kilograms. So that's going to be 20 times 9.8, all divided by 2, plus mass of the sine, which is 5, times 9.8, all divided by the sine of 40. Can you do that one in your head?
Unfortunately, no.
So,
I almost got it.
I think 50. No. That's gonna be way more than
104.6?
4.6?
5.7.
That sounds different from what they told me last period.
Nope, I'm in radians. No, it's
Yeah, 229.
That's probably right.
229 newtons we are calculating a force.
Indeed.
I think you're right. I think you can do this. We're going to use rotation anyway. Though. So using rotation, we can do that to calculate the tension force. Notice by choosing our axis of rotation on the normal force at the application point of the normal force, we've eliminated the torques created by the normal force, so we don't need to worry about it. And so we can calculate what that tension force needs to be. And then part B says find the horizontal and vertical components of the force the pole exerts on the metal beam. So now we can use translational motion equations to figure out that stuff, right? Because I know the normal force has a component that points up here. So that's the normal force in the y direction. And it has, let me use green for my components. Normal force in the y direction, and then I have the normal force in the x direction. So that's what part B's asking. Okay, go. That's what part B's asking about. So I can say now the net force in the x direction equals 0. Well, the net force in the x direction is just a positive normal force in the x direction minus the x component of the tension force, right? If I decompose that, this is going to be F tension in the x direction, F tension in the y direction. So the normal force in the x direction minus the tension force in the x direction equals 0. Or the normal force in the x direction equals the tension force in the x direction. And we know the tension force in the x direction, that is going to be the, if I draw it here, it might be a little easier to see. That's the horizontal component of theta. So it's the cosine component of the tension. So that's going to be the tension force which we just calculated times the cosine of the angle. And so the normal force in the x direction is what we already got, 229, 228.69, yada yada, times the cosine of 40.
175.8.
175.
Sorry.
175 newtons. What time are we out of here? Oh, wait. Okay. All right. And I'm going to leave calculating the y component as an exercise. Just note that it's just a Newton's law for using Newton's laws for translational motion. These two, the sum of these two forces have to equal the sum of the upward components of the normal force and the tension force, right? So just like I did net force in the x direction equals 0, you then have to do the net force in the y direction equals 0, okay? Yeah. All right. I wanted to stop there because we're kind of running low on time, and I want to show you a couple other examples of how we can apply these concepts to situations that we wouldn't otherwise be able to analyze. And these are definitely problems that you'll see on the Quest assignment in engineering classes when you take them in college. Hello. And we'll come back to that. Okay, a pretty common problem is you got a bridge, and there's going to be a truck that's going to drive over the bridge. And you probably, and this is obviously very simplified, but you got two supports and a bridge, and the supports are exerting normal forces on the bridge that point up, and as the truck drives over the bridge, those normal forces are actually going to change. The net force pointing up will have to be the same. It'll have to be the two forces from the supports pointing up have to offset the weight of the bridge and the weight of whatever's on the bridge. But where the objects are on the bridge will dictate what size each normal force is. That should make sense, right? When I have this block over here, which support do you think is exerting a larger force on the bridge, the left or the right? Was it?
Oh, on the bridge.
The left.
Yeah.
Yeah. This support is exerting more force on the bridge because it's supporting more of this truck, clouded truck, than this support is, right? So, forgot what number it is, but number 7 or 8 or something like that. Sorry about the glare on the board at home, guys. So, here's my object. My bridge is my object that I need to draw my free body diagram on. Right there. So the free body diagram for my bridge here, I have a normal force 1, and then I have a normal force 2. And as you guys said, normal force 1 in this case should be larger than normal force 2. I have the weight force of the truck, so MTG, mass truck G, and then the weight force of the bridge itself drawn from its center, MBG. And if the question said, how much force is the left support exerting on the bridge? And all it gives you is the mass of the bridge and the mass of the truck. With normal translational motion Newton's laws, you wouldn't be able to answer that. Because we have two unknowns, and we have no forces in the x direction, so we can't write an equation about the forces in the x direction. So we can only write an equation in the y direction which says that this force plus that force equals the sum of those two forces. And we have two unknowns there. So we have to use rotation here. Again, there's no actual rotation going on. So we just have to choose a convenient axis of rotation and then say that the net torques about that axis of rotation have to be 0 if the system is not rotating about that axis of rotation or it's not accelerating in any kind of rotation. And if the question then said, find what the normal force 1 is, what would be the only convenient, not only, yeah, what would be the only axis of rotation that would allow me to answer that question?
The force normal one.
Yeah. Wait, which one?
The force normal one. The one. Yeah.
This one?
Yeah.
If I'm asked to find that?
Oh, never mind.
If I'm asked to find the normal force 1,
The second one.
if I choose this as my axis of rotation, then this guy goes away from the equation, right? So I got to choose this guy's axis of rotation. And again, this is the only one that'll help you in this case. Because if I choose this as my axis of rotation, then that eliminates this unknown from the resulting equation that I will then generate, leaving this as my only axis of rotation. This is my only force, only unknown. Oh my gosh. Is it Friday? Please tell me it's Friday.
It is.
This is the only force, the only unknown that will end up in my net torque equation. Okay. So again, I'm not going to work this out, but I got a normal or lever arm there, lever arm there, lever arm there. Generally, you're given information about those lengths in the problems. But yeah, if I know all that stuff, and notice if I choose this as my axis of rotation, the torque created by these two forces is offset by the torque created by that force. If I was to pick, because it's arbitrary again, if I was to pick the center of the bridge as my axis of rotation, then I eliminate the torque from the weight of the bridge itself. And then normal force 2 and MTG are actually in the same direction as far as torque goes. And the torques that they create are offset by the torque that normal force 1 creates. Right? So you can kind of conceptualize that and think about how they're fighting the rotations regardless of what axis of rotation you choose, then you'll be able to understand this a little better. All right, so that's the bridge problem. Some insight into helping you answer those questions. The other really common one, and this one's a little more complex. Put it over here. Sorry, this is where it looks, there's less glare. I'm going to put it here because there's less glare for the students at home. This is the ladder problem. Here I just have a ladder, but there are some problems where you got a ladder and then you got someone standing on it at some point. So their weight will actually factor into it as well. So ladders, have you ever been up on a really tall ladder? It's kind of scary, right? You're always afraid that the feet are going to slide out and you're going to fall. Guess what? You can use physics to calculate what maximum angle can you get with that ladder before it's going to slip out. Right? You can do that. But let's just say it's just a ladder. You haven't climbed up on it yet. And it's leaning against the wall. And typically the friction between the wall and the ladder itself, it's pretty negligible. It's another friction, the other friction that actually is real important in keeping it from slipping out from under you. But let's go ahead and draw all the forces that are acting on this ladder. So first of all, I got the weight force of the ladder itself. So I'll call that MLG. What other forces I got acting on the ladder?
The force normal from the wall.
Force normal from the wall. That's going to point to the right. And I'm going to call that Fn1 because I have two normal forces acting on this ladder. What's the other one?
The force normal from the ground.
Force normal from the ground. And notice that if there's no person standing on the ladder, this normal force should be exactly equal to the weight force of the ladder itself. If there's a person on the ladder, then they have a weight force, and the normal force will obviously go up, right? Now, those can't be the only forces acting on the ladder, because if they were, the ladder would be accelerating to the right. So that would be like this happening. So that's not happening. So what force is preventing that? What force is preventing that from happening?
Friction.
Yeah, the friction between the ground and the ladder. Exactly. How did that happen? There we go. So yeah, there's a friction force that's acting in this direction. And that friction force actually needs to be exactly the same size as the normal force, right? Because they have to offset each other. All right. Now, in this kind of a problem, generally you're given, say, this angle, the angle between the ladder and the ground. And then they might tell you the weight of the mass of the ladder. And that's it. They'll just tell you the mass of the ladder and that angle. And they'll say calculate the normal force that the wall exerts on the ladder. Now, the friction here is negligible, generally. It's generally pretty negligible. Usually the problem will say, assume the friction between the wall and the ladder is 0. And then it says, calculate the normal force that the wall exerts on the ladder. Maybe not even normal force. Maybe it'll just say, calculate the force that the wall exerts on the ladder. And all it tells you is the mass of the ladder. Okay. So, but then you think to yourselves, well, friction, I don't know the friction force. Not given any information about that. I'm not given the normal force. Right? I could probably figure out the normal force, but I can't figure out the friction force. So how am I going to figure out that normal force without knowing the friction force or anything about it?
Rotational equilibrium.
I use rotational equilibrium and choose, again, a convenient axis of rotation. What would be the most convenient axis of rotation here? Where your life goes?
The friction force and the force normal second.
And only one person's at. Oh, I guess some guys in the back are saying some stuff. This! The only axis of rotation that'll allow me to solve this question. Because if I choose, notice that's a real convenient one because it eliminates two forces, or the torques created by two forces. So about this axis of rotation, we have the torque created by this normal force being balanced by the torque created by the weight force. Now we must be careful though, because the lever arm for the ladder's weight force is this. We'll call that RL. The lever arm for the normal force up here, which I'll call R for the force normal 1, the angle there is the angle theta. What's the angle between the lever arm and the weight of the ladder? Is it theta?
No, it's
No.
the other one.
It's the complementary angle to theta. So technically that would be 90 minus theta. So you can't use that. You gotta be careful. You gotta use your geometry here. Gotta use your geometry. Okay. And again, we don't know the length of the ladder. So really, what I should have done, why did I not do this?
Just say that's
I'll blame Kurt. I'll just say that the length of this lever arm is the length of the ladder L. So the length of this lever arm would be the length of the ladder divided by 2. And then when I write the equation for the torques created by those two forces, L cancels out also. Okay. Just like it did whenever we did the other one. The bridge one? Is that the bridge one? I don't know, it's been a while. No, the beam one. The beam and the sign. Woo! You said it is Friday?
it is correct.
Okay, good. Alright, that's it. You got a quest assignment. We're going to work on it on Monday. It's due Tuesday night. You will see ladder problems and bridge problems on it. So come with some questions on Monday. Have a wonderful day.